This video is the last in the series of videos demonstrating performance and capabilities of the sci-fi version of Foucault Mini-Dyno, the benchtop precision laboratory dynamometer for testing electric motors and robotic actuators. So in this video I am going to demonstrate how the system responds to slowly changing signals, and since this is an open sci-fi version of the system, unlike the one we have developed under National Instruments Lab, we don't have automatic sequences just yet, so I'm going to be setting set points in sequence using controlling computer at a relative rate, and we'll be giving some comments on how the system is responding. We will be going to recording the display from the Mini-Dyno microcontroller, and also another camera will be looking at the system from the top, showing the operation of the stepper motor that is responsible for the variable air gap of the variable air gap permanent magnetic eddy current brake. And also you will be able to see the display of a torque sensor that is talking with our microcontroller or via RS485 and the Modbus protocol. All right, so currently we have a set point of 10 milliNewton meters, and that's a sensible low point. And just to give you context, the motor under test is not particularly strong, so 50 to 60 milliNewton meters is already making the motor to exercise very hard and perhaps overload it. So 10 milliNewton or 1 milliNewton meter is already quite a substantial load in that context. Not big, but not small either. All right, so I'm going to slowly spin up the motor to perhaps 250 RPM. And then we will start changing the signal in increments of 1 milliNewton meter, and we will see how the system response changes as the torque becoming greater and greater. All right, let's start. Okay, as I am speeding up the motor, you can see that the stepper motor is doing its job, so the variable air gap is becoming bigger and bigger. We are already at 300 RPM, and let's set the system to perhaps, originally I wanted to set it to 250, but since I'm already past 300, let's set it to 400. That's another reference point. Alright, as you can see, the gap is really big now, it's really wide, and the system is maintaining the set point is already almost there, even though it needs to be noted that at this very wide air gap, electromagnetic torque induced by the gap, and the gap is really big, I can actually put a finger between the rotor and the stator easily, the sensitivity is really low, so it's really hard. The algorithm has to work very, very hard in order to just get that coupling, electromagnetic coupling, and get that feedback from the system in order to do something like apply some sensible controlling action. So it is a really difficult task for the system, and you can see the system is almost all the way back because it's still trying, and I think in this situation the some sort of friction in the system dominates, so it can't really adjust anymore. So let's give it something to work with. I'm increasing the set point to 20 milliNewton meters, and probably at this point it will start doing something, because we really would like to overcome the baseline. Still not yet, but it starts to gradually move forward. But like I said, there is some offset in the system that is not of electromagnetic nature, and therefore the algorithm has certain difficulties adjusting. All right, let's make it 3 milliNewton meters. And I think now we are starting to move somewhere, because now the system is moving into the range where it can very efficiently maintain the set point, and it's still a little bit confused, should I say. but it's trying. So the little guy inside of the microcontroller enclosure is trying their best in order to reach the set point. But normally when we are in this range of air gap about well over 10 millimeters, since sensitivity is very low, electromagnetic braking sensitivity, or the whole electromagnetic coupling between the rotor and the stator is so weak that it's very, very hard for the algorithm to actually start regulating properly. But now we are really, really getting close, and as you can see, it's doing its job and it's actually taking its time. And we are at the set point, or almost. But once we are within this range, you will see that once we are within the measurement range, this is where the system will be extremely responsive and fast. All right, now we are at 3 millimeter meters, and we are in the range. We are in the range like less than 10 millimeters. This is where the interesting stuff starts. This is where electromagnetic braking torque dominates all other small linear or non-linear effects, that resistive effects that might be in the system but not explicitly accounted for. So now we are in this electromagnetic braking range. Let's give it another millimeter meter. 40, and now it keeps moving. Are we there? Not here yet. Few more seconds. And we are almost there. Yeah, we are there. Let's give it a bit more. 5. And now, you see, now once we have just entered this range, then several seconds, and normally, according to our specs, when we are within the control range and like well confidently within the measurement range of our torque sensor, because certainly there will be also some certain offset in the torque sensor itself, uncontrollable drift of zero and those kinds of things. So once we are well within the range, and this is like 5 millimeter meters for the torque sensor, is well within the measurement range, and also well within the physics dictated by the Faraday's and Lenz's laws. Now the control becomes extremely responsive, and let's just start ramping. 6. 7. 8. 9. And now the motor on the test is start to actually work out pretty hard, and actually it seems to be starting to slow down a bit, and we are going to 10 millimeter meters. Now we are pushing hard on the motor, and within this range, very small displacement of the stator will cause substantial changes in the torque, and therefore the algorithm has the ability to adjust extremely fast, because it doesn't even have to travel that far. The stator doesn't have to travel that far to achieve significant changes. Essentially, for this particular machine, approximately 2 millimeter travel increases the load about 3 times increase, and if we go in 3 millimeters away, it reduces the current resistance level at the given speed approximately factor 3. All right, and then let's try to make it. Maybe let's get it with increments of 1. Let's make it to 20, and then we'll do something more interesting. All right. 11. 12. 13. 14. 15. 16. 17. 18. 19, and 20. All right, we are at 20 millimeter meters already, and as you can see, once we are within this solid, like real, serious load range, the algorithm adjusts the load really fast, and so those small increments can be achieved in a matter of just like a few seconds, and we feel like even faster than this. According to our general spec, we are normally doing it within between 2 and 6 seconds. But when this is for step response, but for very slow changes, it can be anywhere between perhaps 1 and 2 seconds or so. And this is what's actually the practical measurement range. So now I'm going to apply a little bit like extra 2 times. I'm going to make it 40, and this is going to be very hard on the motor. And then we will try to see how the step response changing from the 20 millimeter meters to 40 millimeters, changing 2 times from one serious load level to another serious load level. How many seconds will it take to stabilize, for the control algorithm to stabilize at 40 millimeter meters? And let's just do it. 3, 2, 1, go. 1, 2, 3, 4, 4 seconds. So in 4 seconds, we have managed to make the transition between 20 millimeter meters and 40 millimeter meters. And now let's do, and we already just take note that the air gap is already less than a millimeter. We can still go a little bit further. We can still get probably to, at this speed, to perhaps 70, 80 millimeter meters with this theta configuration before the system hits the end of the physical range. It's not allowed to move closer than 0.1 millimeter to avoid mechanical contact. But we are going to go now all the way down from 40 millimeter meters to 1 millimeter meter, and we'll see also, we'll observe how quickly the system will find a new stability point if we are introducing 400% change in the resistance level. And please pay attention to what is going to be happening with the stepper motor and with the stator. Sometimes it can surprise you with very fast movement. I don't know if it's going to happen now or not. Well, not today. Still pretty fast, but not extremely fast. And yeah, practically there. 100, and let's just do it a couple of times. We'll count seconds. Back to 40, and 1, 2, 3, go. 1, 2, 3, 4, 5, 6, and I would imagine we're already kind of there. Yeah, almost there. Yeah, 8 probably seconds. It's hard on the motor, and also it is important to understand that the motor is also having a hard time to put out the torque, so the motor seems to actually reacting in its own way, so it is interaction of 2 systems. But when we are releasing the load, normally the releasing of the load is much easier. So we went from 440 to 10 in perhaps several seconds, 2, 3 maybe, and then from 1 to 3, well, from 10 to 4, it just took us perhaps about 8 seconds. And let's just maybe slow down the motor, and we will see what's going to be happening as I'm gradually slowing down the motor with this level of load. So the dyno will keep tracking the speed change and will keep trying to maintain the set point until the gap is too narrow and it's not allowed to move any further. And this will be the slowest speed achievable on the system while outputting 40 millimeter meters. So the gap is now really tight, but we still have a little reserve. I would imagine the system will hit its limit at perhaps 250 RPM, but we will see. 0.41 millimeters the gap. Slow a little more. And we can still do that quite substantial torque for this type of the motor. So to those who are more used to the servo motor or geared motor terminology, 40 millimeter meters is approximately 410 gram per centimeters. So now we are still doing it, 272 RPM, we're still doing it, but the gap is very close to its limit. I'm going to try to change the speed really slowly. And that's it. The system can't go any further because now we are at 0.12 millimeter gap. And with this, at this speed, the next controlling action would push the system closer than 0.1 millimeter, and we certainly don't want that to happen because this is where the real risk of mechanical contact occurs. So the system is robust and will not attempt to do what it is not able to do. So this is where it stops. And now I'm going to just push it back. I'm going to try to show you extremely fast motion of the stator. I'm not sure if I'll be able to achieve it or not, but I'm going to change set point to 0.005 Newton meters or 5 millimeter meters, and we'll see what's going to happen. 3, 2, 1. The system didn't do what its creator has requested, but it's still performing really well. So we are already at 5 millimeter meters, maintaining it stably and nicely. So this is the dynamics of the system. So if you have any motor that requires some type of modulated load, for example, mission specific profiling of the load, or you would like to implement some sort of mapping, efficiency mapping, for example, this is where our system can help a lot because it can adjust its load in response to the set point, to the reference signal, really fast and precise, and therefore it is suitable for a lot of automated testing sequences and also for all other sorts of high precision laboratory testing of motors, be it propulsion motors, robotic actuators, or UAV motors, or alike traction or propulsion motors. Thank you very much for watching, and if you would like to get in touch with us, discuss our application, or make a purchase request, please refer to the description of the video, to the email in the description of video, and thank you for watching. Hoping to hear from you, and please leave a like, and if you like this video also, leave some comments. Thoughtful comments are very much welcome.